Hello students, in today's lecture we are going to derive the relation between differential cross section and scattering amplitude. Here we have an incident particle and a target particle. The mass of the incident particle is m1 while the mass of the target particle is m2. But in quantum description, the incident particle is represented by a wave function. And we know that here the incident wave function is a plane wave having a wave vector k0. When it interacts with the target potential, here we have some potential. The target particle in quantum mechanics is represented by a potential. So when the incident wave interacts with the target potential, then it scatters. Here these black lines, the circular lines, represent the outward spherical scattered wave, while some of the incident wave goes along the z-axis unscattered. Here we are going to calculate the differential cross section by the number of scattered particles here through this solid angle d omega, and which are interacting or intersecting this surface, which is dA. In our first lecture at the start of the chapter, we defined the differential cross section as the number of particles scattered into an element of solid angle d omega in the direction of theta phi per unit time and incident flux, and is written as d sigma over d omega, which is equal to 1 upon j incident into dn theta phi over d omega. That this is equation number 1. This equation is the basic equation for the differential cross section, which is the number of particles scattered into a solid angle in the direction of theta and phi per unit time per incident flux. Here this j incident, this is called the incident flux, and this dn it represents the number of particles scattered into an element of solid angle d omega in the direction of theta and phi, and it is intersecting a surface element which is dA per unit time. This dn in the expression, it represents the number of particles scattered into an element of solid angle in the direction of theta and phi, which is intersecting this surface per unit time. And this is given as this dn theta phi, it is given as the scattered flux density times the area element. Clear? And the area element is r square into d omega. So if we write it as this, dn theta phi will be equal to j scattered into r square d omega, or we can bring this d omega to the left side. This will be dn theta phi divided by d omega, which is equal to j scattered into r square. This is equation number 2. Here let me tell you, our job is to find this d sigma over d omega, which is the differential cross section, then for which we have to calculate this term, which is dn over d omega, as well as the incident flux density. So first of all, we are going to calculate this term, which is dn over d omega, which is using equation number 2. Here this j scattered, it represents the scattered flux density, and by definition the scattered flux density is given as I h cut over 2 mu into phi scattered times the gradient of the complex conjugate of the scattered wave function minus the complex conjugate of the scattered wave function times the gradient of the scattered wave function. This one is equation number 3. Now we have to calculate this term, and then we have to substitute that value in equation number 2. Therefore, in our previous lecture, we defined the scattered wave function as the scattered wave function was equal to a times f of theta and phi exponential I k r divided by r. Here this a is called the normalization factor, and f of theta phi, it is called the amplitude of the scattered wave function, and k is the wave vector of the scattered wave. Similarly, its complex conjugate will be equal to a f of theta and phi into exponential minus I k r divided by r. Now we are going to calculate this term. Therefore, the scattered wave times the gradient of the complex conjugate of the scattered wave will be equal to, here the first term in equation number 3, it will be equal to, the scattered wave function is a into f of theta and phi times exponential I k r over r into the gradient of this one, the scattered wave function. So its gradient will be a f of theta and phi into, take the derivative by using the quotient rule, it will be minus I k into e to the power minus I k r into this one, which is r, minus derivative of this one into this term, so its derivative will be equal to 1. Therefore we will get e power minus I kr divided by r square. Clear? Now multiplying this term with this one as well as this one, so we will get this as a square, a mod square into f of theta and phi mod square. So when this term is multiplied with this one, clear? So it will be minus ik and e power ikr, e power minus ikr. Clear? So it will be 1 and divided by r multiplied by r square, so it will be r cube and 1 r will be cancelled with this r, so we will be left only with r square. And similarly, when this term is multiplied with this exponential term, we will get 1 upon r cube. So this is now equation number 4. Clear? Now the last term of equation number 3, it will be, which is phi complex conjugate of the scattered wave times the gradient of the scattered wave. So the complex part is a into f of theta and phi exponential minus ikr divided by r times the gradient of this one. Clear? So it will be a times f of theta and phi, and it will be derivative of this one, which will be I k into multiplied by this term r, and it we will get e power I k r minus derivative of this one, which is 1, and times this one I k r divided by r square. So now multiplying this with this one, so this will be equal to a square f of theta phi square. Similarly, when this exponential term is multiplied with this term, so we will get ik divided by r square, and when this one is multiplied with this term, so we will get minus 1 upon r cube. This is equation number 5. Now putting these two values here, this one is phi scattered times the gradient of the complex part of the scattered wave function, and this is the complex part of the scattered wave function times the gradient of the scattered wave. Clear? So substituting these two expressions in equation number 3, we will get j scattered using equation number 3. J scattered will be equal to I times h cut divided by 2 mu into this term is a square f of theta phi square into minus ik divided by r square minus 1 over r cube minus a mod square f of theta phi mod square and ik over r square minus 1 over r cube. Clear? Take these two terms out of the bracket, so it will be I h cut divided by 2 mu into a mod square f of theta phi mod square, and here we will be left with minus ik divided by r square minus 1 over r cube, and similarly when this negative term is multiplied with this one, so we will be left with ik divided by r square, and it will become positive 1 upon r cube. Here this negative 1 over r cube will be cancelled with this term, and this will be minus 2 ik over r square. I h cut divided by 2 mu a mod square f of theta phi mod square into minus 2 ik over r square. Here these two is cancelled with this two, and I into I, it is minus 1 times this negative, so it will become positive. So the scattered wave will be equal to, the scatter flux density will be equal to plus h cut k divided by mu into r square times a mod square into f of theta phi mod square. That this one is equation number 6. So we have found this term, which is equation number 3. Now substituting it in equation number 2. Substituting equation number 6 in 2, put 6 into we get. So this r square will be cancelled with this r square, therefore dn theta phi over d omega, it will be equal to h cut k times divided by mu times a square into f of theta phi mod square. This is equation number 7. So we have found this term, equation number 1, this term. Now we have to find the incident flux as well. Similarly, the incident flux is given as, now the incident flux is given as I h cut divided by 2 mu into the incident wave function times the gradient of the complex part of the incident wave minus complex part of the incident wave times the gradient of the incident wave. That this is in equation number 8. So by the same way we have to find this term first and then this one. Similarly, Again, in our previous lecture, we defined the incident wave, which is a plane wave, as a times e power I k naught into r, because the wave vector of the incident wave was k naught. Clear? And its complex conjugate will become a times exponential minus I k naught times r. Therefore, this part will become phi incident gradient of the complex conjugate of the incident wave. It will be equal to a e power I k naught into r times its gradient will be minus I k naught into a e power minus I k naught into r. Clear? So by multiplying this term as well, we will get minus I k naught into a square. Clear? This will become 1. This is equation number 9. And similarly, the second term will be phi steric del phi. This will be equal to a exponential I k naught into r times its derivative will be equal to a times I k naught into exponential I k naught into r. Clear? Now multiplying these two terms, we will get a mod square I k naught. This is equation number 10. Now substituting these two values in equation number 8, we will get J incident, put equation number 9 and 10 in 8. The incident flux density is IH cross over 2 mu into this term, which is minus I k naught times a mod square, minus this term, which is a mod square I k naught. Clear? So it will be equal to I h cut over 2 mu. This will be minus 2I k naught into a mod square. This 2 will be cancelled with this 2, and I square, it will become square. So this negative sign will become positive. Therefore we will get h cut k naught divided by mu times a mod square. This is the J incident. This is equation number 11. So we have obtained our two important results. This equation number 7, equation number 7 and equation number 11, and now we have to substitute them in equation number 1 here. This is equation number 7, which is dn over d omega, and the J incident is h cut k naught over mu into a square. Therefore now we have to substitute them in equation number 1. Put equation number 7 and 11 in equation number 1, which is d sigma over d omega, which is equal to 1 upon j incident, which is equation number 11. Listen, h cut k naught or mu times a mod square into dn or d omega, dn over d omega, which is h cut k divided by mu times a mod square into f of theta phi mod square. So here this h cut over mu will be cancelled with this term, and similarly a square will be cancelled with this one. Therefore we have d sigma over d omega, which is k divided by k naught times f of theta phi mod square. This is equation number 12. So this is our final result which we have obtained, which is for in case of the inelastic scattering. So if the scattering is elastic, for elastic scattering, for elastic scattering, k is equal to k naught. So these two terms will be cancelled and we will be left with d sigma or d omega, which is the square of the mod of f of theta phi. This is equation number 13. This is our final result. Thank you very much.